divide code this. We'll see what happens, and see like whether or not the decoding looks stable. Yeah, but for routing, that'd be like pretty interesting as well. I feel like there's a lot of stuff to do with the router, honestly. It's like open on how best to train in. Like even when people were you there for the next Olmo talk? Oh, there was a talk, she talks about just talking about routing the whole time almost. It was basically how to add new experts like on the fly. It wasn't clear how to train the new experts. Coordinate with other previous experts.
Okay. Thanks everyone for staying until the last talk of today. So now we have Maryam Aliakbarpour, who is a professor at Rice University, and she works on differential privacy, statistical learning theory, and theoretical computer science. And today she will talk about mean estimation for heterogeneous and unreliable users.
Thank you for the introduction. So today I'm going to talk about mean estimation from heterogeneous sources of data. So the standard point of view of data that we all hold near and dear is we view data points.
For some reason, it's just
I don't, they can't hear me. Is it better now?
Yeah. We'll see.
Okay, I think that, okay. Okay, if my voice went down, tell me and I will, okay, perfect. So the standard point of view is that we view every data point as an IID samples from one distribution, and we usually view data set as a pool of these samples. And in reality, these samples are collected from various sources. So it could be different individuals, different institutions, or different even devices contribute to creation of data. And then what we see as one single data set is actually coming from multiple sources of data. And it is often the case that these sources provide more than one sample. So they give us essentially batches of samples. So what we usually see is that these batches could vary in quality. So for example, some of these batches could be very relevant to the statistical task that we have at hand. Some of them might be less relevant, or even some of them could be maliciously corrupted. So a user intentionally feed us wrong or bad data. So what we want to do is essentially do inference in this chaotic setting where we don't have consistent sources of data. We don't know which source is trustworthy, which one is not. It is often an important question, how do we even model this setting? Like, how do I actually talk about this variety in the source's quality? And when we are doing inference in this case, obviously we want to benefit from the fact that we have multiple sources of data. We want to do something that each individual source cannot do on their own and benefit from the collaboration. And in particular, if there are a certain number of good quality samples and in the total data set, I still want my error to degrade with the total number of good samples and not with the number of good samples per sort of good batches. And we also want this robustness that I talk about. So I want to be robust in terms of some level of corruption and malicious data points. So let me start by telling you about our model, which tries to answer this question that I mentioned. So we inspired by the work of Qiao and Valiant, we are using this untrusted batch model. So what does this model says? It says there are T many users, each of them come with n data points, so each batch contains n samples. And each of these batches are essentially have two quality. Like I can talk about two types of quality in this batches. Some of them are good and some of them are bad. And when I'm saying good, it doesn't mean that they are perfect from the distribution that I want, but it means that they are sufficiently relevant to the statistical task at hand. So for the paper of Qiao and Valiant, this was parameterized by a distance parameter, like a TV distance bounded or like AK distance bounded. We're going to deviate from this, and I'm going to explicitly define what do I mean. And then we have a bunch of samples that are adversarially corrupted. So this is essentially a two-value approximation of the trustworthiness that we had in the previous slide. So instead of saying things are perfect, I'm going to say, okay, things are decent, and some of them are even bad and malicious. So like decent and bad, basically. And then when I talk about adversarial or malicious, I mean a strong contamination model. So this is essentially one of the strongest contamination model that one can think of. It's, if you have heard of Huber and other contamination model, this is pretty much the strongest contamination model that we have. The way that this contamination works is that the data set, according to the clean samples, are generated. This data set is given to the adversary. The adversary maliciously tweaks some samples according to its budget and then return the data set. So it's different if we say that random samples comes from an adversarial distribution, because there is some randomness in that. In this case, the adversary can even erase some information from our own samples and make us to believe something else. So the problem that we study is mean estimation in this setting. What we have is that there is an underlying distribution P that we are trying to estimate the mean of P. The mean is denoted by mu and the covariance is denoted by sigma. These parameters are unknown, but we know that sigma is bounded by identity. What we want is an estimate mu hat such that the L2 norm between mu hat and mu is bounded. And we want a high probability bound, like let's say it's bounded with probability 90%. So you probably have seen this problem in the standard setting. If there is no corruption, no batches, just one big data set. If the covariance matrix is indeed identity, what happens is that most of the points are going to lie in this sphere of radius square root d, and if we take the empirical, it's going to fall off a square root d over n away from the true mean, and you can show this is indeed optimal too. So our first model.
Just to make sure, are we also assuming big sigma is like PD because we are trying to count the L2 of the mu, or can big sigma have like zero dimensions?
I see. I think it's worst case, so it could, like we don't have any extra assumption about that if it lives in a lower subspace.
I see, so the bound will depend on big sigma.
No, because I upper bounded by this.
This is like a variance upper bound. It's just like the problem has upper bounded variance, and then so if it lies in a low-dimensional space, square root d still holds as an upper bound.
No, I was just saying that we are trying to estimate the real mean in L2, not in the metric induced by big sigma, so we might not see some directions.
No, but I upper bounded by 1, right? Okay. I think if you know more information about sigma, you can do something better. But if I don't have anything other than it's upper bounded, this is pretty much what I end up with. Okay. So now I want to talk about. So remember that I told you there are good users. There are somehow related to the underlying distribution, and then there are malicious users. But let me tell you what I mean by good users and how they are related to the underlying distribution. We study 2 models, and this is the first model, which is min-shift model. So in the min-shift model, each user has data from some distribution pi with mean mu I, and again, bounded variance sigma I. Again, mu I and sigma I are not known, but sigma I is still bounded. What we have is that these means are not too far away from the true mean that I want to recover. So each of these distributions are shifted by at most the square root alpha. And each of them draw their own sample. As you see in this picture, they might have different covariance matrices. But what I see is essentially a collection of these guys. And then I have some bad users. I don't know which user is good and bad, but they gave me another data set, and I don't have any upper bound or any assumption on how these points are, so their covariance could be very large. So what we can prove in the min-shift model is that one can recover mu hat with error of square root epsilon over n plus square root alpha plus the square root d over tn. Let's just go through these error terms one by one. The first one comes from the corruption parameter. What is nice about this corruption parameter is that as I have more samples per batch, my dependency to the corruption parameter goes down. So remember, the batch structure is really nice because it tells me if I somehow figure out a batch is good, then I have a lot of good samples chunked together. So it's like it has a lot of information for me. And this is exactly where the batch structure plays a role. The larger the batches are, I'm going to get a better benefit from this. The square root alpha is kind of necessary because let's say all the sources are shifted in one direction versus the case that sources have a shift equal to 0. So you cannot, there's no information to essentially be able to approach mu without better than this square root alpha. And then this is the bound that we saw. The last term is just the bound that we saw for the empirical mean estimation. If I have t times n many good clean samples, I still have to pay d over tn. So our sample complexity is optimal as long as this error is smaller than 1. So for this algorithm to work, we need d many samples. But from after d, the sample complexity is d over this error term squared, which is optimal. Again, by the same analogy that we have, that d over the error can be at most d over the number of samples, or square root of d over the number of samples.
So T is what? The total number of?
T is the total number of batches, and N is the number of samples per batch. So Tn is my total number of samples.
Okay.
Yes.
If it's batch algorithm used to the usual statistics setting?
We will, let me tell you about the solution, and if this did not answer your question, we can talk about that.
So here you say when T is not too large. Is that how I should read it?
No, T should be, when T is not too small, so T has to be larger than D. When T is less than D, like significantly smaller than D, then our robust part doesn't quite work.
So Tn is omega of my reading?
Yeah, I think coming from a TCS community, this is an upper bound, so that's why I showed it with O. But yes, T has to be larger, yes. It's like the sample complexity of algorithm is equal to at most this bound. That's what I meant by O. Okay?
I have a question about the model. Like, could I get some similar bound by in the single distribution model, considering a mixture of distributions? Does that make sense? You consider many distributions.
Mm-hmm.
In the single distribution model, I give you a mixture.
I see. So what happens if I pull everything together? So then, I think going back to the question that another person has, so if you just treat this as a whole, then the corruption level is epsilon, and you don't get this this n in the denominator. So square root epsilon would be necessary if you just treat it as a giant batch of samples. And again, I'm not sure, because of this heterogeneity, I'm not sure. I mean, you can think of it as a mixture, sure. But generally, if you just treat everything as just one giant batch, you don't get this n in the denominator.
So should I read that? I'm so confused about. Should I read this condition as just Tn greater than D? Because you have, it's sort of, the error is itself in terms of T and N, and so it's hard for me to...
Okay, fair question. So I am saying, so my, in the setting that I have, so alpha and epsilon over n are smaller than 1. For me, if this other term is also smaller than 1, everything is optimal. And what happens when this term is smaller than 1? Always d over epsilon squared is the dominating term. So what I'm writing here is that this is basically saying when error is smaller than 1, the dominating term in the sample complexity is d over error squared, which is optimal, and then the error is also optimal. Does that make sense? But then, when the number of samples is smaller than d, I have no guarantee, basically. And in that case, this term is going to be larger than 1. Right? Okay. Sorry, I thought if I write it this way, it would be easier. But you could also think about that for robustness, you need some minimum number of samples, and then the sample complexity is what you want. Okay, so our second model is this thing I call double corruption model. So everyone is going to draw n samples from the underlying distribution, and then an adversary get to corrupt beta fraction of the samples that we have. So for example, if the adversary wants to shift the mean from mu to mu prime, it can delete the data that existed in here, add some data in here, and make the data set to look like have a different empirical mean. So this is why I was saying that this is a very strong contamination model. And now what we see from the good or relevant users is a bunch of these sets that they are contaminated, potentially shifted in different directions. And then we have some bad users that their data is essentially arbitrary. So just to get a sense of the corruption level, like if you have a standard, if you put this thing in one data set, so this row is the data of user 1, this row is the data of user 2, and so on, this corruption model says the adversary can corrupt epsilon fraction of the users, and even from the good users, it can corrupt beta fraction of their samples. So the overall level of corruption, if you just think of this as one big data set, would be beta plus epsilon, or order of beta plus epsilon. So again, in this case, what we have shown is the error is proportionate to a square root beta plus d over Tn. Again, I have the same situation with the sample complexity. This error is optimal, and you might wonder, okay, why the epsilon over n does not show up here? The epsilon over n is actually in there. The thing is that because beta is always at least 1 over n, because I have to give the adversary the budget of corrupting at least one sample, otherwise the problem is just going back to the previous case, then epsilon over n that is in here is being dominated by this square root beta. And again, all of these terms are optimal as long as the omega, as long as the number of samples being omega of d. Okay, any question? Yeah, that's the result.
What is the adversary allowed to corrupt? Maybe I didn't follow that
So it's the adversary just has a budget of the number of sample it can change, but there is no assumption about how it will change the sample. Whatever the adversary wants,
Just replaces it with some other sample.
it replaces it with other samples, yeah. Okay. So let me tell you a little bit of background in robust data analysis, especially in robust mean estimation. So when we have a one-dimensional data point, one of the things that the adversary can do is possibly to delete epsilon fraction of the sample on one side and put it in the other side. And there's this sort of a very delicate balance that the adversary needs to follow. If the adversary starts put things too far away, I can just say, oh, these are obviously an outlier. And if it starts putting things close enough, then it also cannot shift the mean by as much. So there's this delicate balance that the adversary tries to do. In the one-dimensional case, the median is a very robust estimation for the estimator for the mean, and it turns out that you can assume, like if you have bounded variance, you can show that the median is actually essentially getting the right error bound. In the higher dimension, the situation is slightly different. Now, if I want to come up with the median, it's kind of the median is kind of not super well defined when you have a high dimensional distribution. You want to pick something that is median in every direction and make sure that it is robust. One proposal is the two-key median. So the two-key median essentially counts the number of points that, for every half a space, for every point x, it counts the number of points that falls in the half a space that goes through x. And in this way, if you consider all the half a spaces and count this number and take the minimum, it kind of tells you, okay, how centered I am compared to the rest of the point that exists. Two-key median is indeed a robust estimator, and it also, you can show it with some caveat. It derives the right error complexity of a square root epsilon, but it requires exponential time to compute. So this is something too expensive to compute. So other alternatives that one might think of is that, okay, I'm going to look at the median at every coordinate, or I'm going to think about geometric median. So geometric median is a point that minimizes the sum of distances to all other points. Those methods are nice. They're polynomial time. However, you can show that they're provably not robust in a sense that the accuracy that would get is epsilon times poly d, which means that you will have a dependence to the dimension in your error. Okay, so the core idea behind robust mean estimation and the relevant paper in this topic is about one observation, that if you find a subset of samples that are large enough and also their empirical covariance is small, you can actually show that the mean of that set is a good estimate for the true mean. If I want to give a little bit of intuition that why this is the case, it's because assume that the empirical mean of your data set is very far away, and you have a lot of good sample in this subset. Obviously, because this mean is very shifted than the original mean of this data, you will see a contribution of large sort of covariance from the good points in your data set. Because in expectation, they had a very different mean, so if you shift that empirical mean by a lot, you will observe this, you will observe a surge in the covariance in every direction. If I want to try all samples, obviously this is going to be another exponential time algorithm, but there are methods such as filtration algorithm and sum of the squares that try to find the subset in a time-efficient manner. So we're going to use the sum of the squares method. Let me just quickly explain what sum of the squares is. I'm going to be very precise on what it means, but generally speaking, sum of the squares is a method for optimization of polynomial constraints. So I have a polynomial px that I want to minimize, for example, and then I have a series of constraints that are polynomial themselves, so f of xi is at least 0 or g of x equal to 0. Or you can just assume that you have one type of constraints. That's also what suffices. And then we want to solve this problem. The issue is that this problem in general is computationally not feasible, and we might not be able to solve this precisely. So through a set of complication, certification, and so on, sum of the square essentially goes after finding a certificate to show that a particular subset of constraint doesn't have a solution, and through that process, it can provide us with an algorithmic object. This algorithmic object is essentially an oracle that act like an expectation. It's a pseudo-expectation, so it's not exactly expectation, but this pseudo-expectation satisfies certain nice qualities that we're gonna use. So first of all, it does not stretch variables, so expected value. So this is, before saying that, this is the operator, so it's like an oracle. I send to it any monomial of the variables that I have in my constraint, and I'm gonna get return, let's say, expectation back. So what it does, it's not going to stretch things, so expected value of 1 is 1. If I give it a squared polynomial, it will return something that is positive. And then it's a linear operator, so if I have expected value of x and expected value of y, that's equal to the sum of them would be expected value of xy. And it also, to some extent, follows the constraints that I have, meaning that if I have in a squared terms times this positive polynomial, it will be positive, and if something is 0, it will remain 0 even if it's multiplied by another polynomial. The thing is that all of these would only hold up to degree k, so I'm not talking about large polynomials, but just sufficiently low degree polynomials are good enough. And then in the sum of the squares, we essentially write the problem of finding that nice set S in terms of polynomial constraints. So basically, I assume that there are some imaginary zi's that I put them as variable in my sum of the squares. These are supposed to be the clean version of the data. And I'm basically asking sum of the squares, can you come up with a clean version of the data? And what we do, we have this WI, which basically says which of the corrupted samples are going to be nice and included in that set S. And for those samples, I assert that if the corrupted sample is VI and I decide to select this sample as a good sample, then ZI has to be equal to VI. So this should be equal to 0. Sorry, I think the equal to 0 part is not here, but basically it says if it is selected, then these two guys has to be equal. And then I also enforce that a large number of samples has to be selected, so they are good samples. And another thing that I want to add is that the empirical covariance of these imaginary nice samples has to be small. So the solution is actually the mean of these imaginary samples. If you think about it, if these are the good samples, then their mean is exactly what I want. To use this sum of the squares methods, I have to prove certain things. I have to prove that one solution exists for sum of the squares. And then I have to also show that if sum of the squares comes up with a solution, it is consistent with the true sample. So I cannot say that the ZIs that the sum of the squares find are necessarily the right solution, I'm going to assume that there is something else, that little zi's are the nice solution, and argue about the empirical mean of these two sets of solutions. So what I require is that the imaginary clean samples should be the empirical mean of the imaginary samples should be close to the empirical mean of the true samples. And then if this is the case, then we know that z bar is also close to the mu, because this is empirical mean of the actual samples. So there is, I have a couple of slides at the end to talk about this identifiability part more, but just for now, just assume that that constraint on the variance will help me to prove this guy. Okay, so let me talk about our constraint for the mean shift part. So the issue is that I have, in the min shift setting, I have a heterogeneous set of distributions. It's not clear when I'm talking about even the empirical mean. What do I mean? Like, because the centers of these guys are different, and what would this imply for the value that I want in the identifiability proof? So what we're gonna do is the following. For the good users, I am going to look at the empirical mean of each of the good users. So these are the samples that I received from the good user. Remember, in this model, at the user level, there is no corruption. So the empirical means are actually nice and clean. This is an empirical mean from mu, with the mean mu I and covariance sigma I. And then the empirical covariance is also bounded, and it's actually nicely bounded by 1/n times identity. So if mu i's were exactly identical, then this would have been a great sample. I have a very stable sample from the underlying distribution, and I would be almost done by just following the standard procedure for robust mean estimation. So here, obviously, we are not exactly in the setting that the mu i's are mu I, so we have to adjust a little bit. So what we're gonna do, we're gonna truncate our samples. So for the sample xi, so this is the true mean of, by sample I mean truncate the mean of every user. So for every mean xi, if it is larger than some threshold, I'm going to just set it equal to mu I, and otherwise I'm going to keep that value. So I'm going to truncate things to mu I. And there are a couple of things that I have to show is that, okay, this truncation does not change the mean of this variable, and also does not mess up with the variance. Hold on those thoughts for a second. And also, I'm not going to truncate too many points. But from now on, I'm going to treat these xi's as my imaginary, or like, as, yes?
So this is just, what you're going over is the existence of a sum of squared solution.
Yes, yes.
This is known as part of the algorithm. You're just saying the algorithm is the SOS algorithm with the conditions you're
Yes.
And the existence of a solution is the first step, and this is what you're going over.
Yes, yes. So what we're gonna do is like essentially treating these xi's as my potential imaginary sample. So I'm coming up with one solution for sum of the squares. In that solution, so we have this truncated samples. If I set this R right, so this is not exactly what we do, but like this is a good, good value to see that for this value you roughly truncate epsilon fraction of the samples. So the truncated sample are essentially can be viewed as an epsilon corruption of the true samples, and the true samples an epsilon corruption of the corrupted samples. So you can sort of say, oh, the two sample sets are roughly theta of epsilon away from each other. And also the mean of this guys is very close to the mean of this guys. So I can also go after finding the mean of this truncated sample instead of the mean of the true samples. Now, in terms of covariance, we can use this advantage that we have, that in the batch structure, if I have many samples from one person, then the covariance is very small, or like it's scaled with 1 over n. So obviously the truncation, because, so you can say, oh, I don't know what mu I is, but this is sort of I'm not going to construct these xi. These are like sort of imaginary. Because I am essentially putting every point closer to its mean, the variance cannot blow up, right? So the variance definitely goes down. And also, here I have them centered around their own mean, but if I try to center them around the mu, the parameter that we want, we're not going to shift this by a lot, just because mu I and mu are alpha away from each other. So I get a very nice sort of, whatever you want to call this, like a shifted covariance from this xi primes. Now I have several of these xi's, and I can show actually the expected covariance matrix of this form is also bounded. So you can imagine that with this trick, I can go back to the sum of the squares and write this in a different way. So now I'm going to use zi's to be this truncated empirical means. And I'm going to enforce that there are at least 1 minus epsilon of the users are good, they're selected as they are, and then the general covariance bound that we saw in the previous slide. I just want to point out that depending on, so remember that we had 3 terms in the error. Depending on which one is the dominating one, we have to pick epsilon in a different way. Sometimes if I pick R a little bit closer, maybe I'm going to throw out more than epsilon fraction, but the benefit that it gives me in the concentration is good enough that I would rather to do that. Depending on which error term would be the dominating one, we will choose a different fraction. Do you have a question?
So the bounded empirical covariance, we get this with high probability, or we get this exactly?
No, with high probability. I think because this is, like the z is also empirical, so with high probability.
But, and I'm not very familiar with SOS. Is it usually sufficient to only satisfy it with high probability?
Yeah, so that is just going to go, like if it's unsatisfiable, the SOS will return garbage, but that's fine. Yeah. So let me quickly talk about so this is, and we're going to feed this to the SOS, and pretty much with the same strategy that the standard robust estimation have.
One quick question, and all the original means were within alpha, or only
Yes.
all of them?
Oh, from the good people, yes, they are all within a square root alpha.
Okay, but
For
how
the
many from the good people did you have?
1 minus epsilon fraction. Epsilon fraction is malicious, 1 minus epsilon fraction are good people. So the majority is good people.
That's all. So the majority is within alpha.
Yes.
Yeah. So the original ones before corruptions were all within alpha.
Yes.
Okay. Yeah, thanks.
So for the lower bound, it's actually not too difficult to see that epsilon over n is a square root epsilon over n is a bound that you will see in the error. Just consider this simple case. If you have 2 distribution, H1 is all on 0, so it just outputs samples from 0, and then H0 is a distribution that has probability 1 minus epsilon 0 in 0, and then probability epsilon over 0 on 1 square root epsilon 0. So with some small probability, it's going to output something that is non-zero. And the idea here is that H1 is all zeros, and in H0, if the adversary receives any samples from H0, it will try to replace the non-zero one with zeros. And after I see the sample set from the adversary, I will see a set of zeros. I have no idea if it comes from H1 and H0. The mean of H1 and H0 are actually sufficiently far from each other. So this is something that if the error is significantly smaller than epsilon over n, we should be able to notice it. And why this is enough is just because the probability that you receive 1 non-zero sample is epsilon 0 times n, and by setting epsilon 0 equal to epsilon over n, it means that the probability of one user having non-zero sample is just epsilon. With Markov, I have only 10 times epsilon many people that will have a non-zero error, and I'm gonna hide all of them and corrupt all of them. I think maybe it's better to put it epsilon over 100 times n, but I think you get the idea. And then the square root alpha, as I mentioned, it's necessary because the case that all of them are shifted by square root alpha and not shifted by square root alpha is just not distinguishable. So
what is the rate at which it's not distinguishable? What is any assumption on alpha? Because
alpha has to be smaller than 1, or like a constant, 0.1, I think. Here.
okay. So sorry to make you go back.
No.
Alpha. So alpha here, you don't have any dependence on dimension for alpha.
No.
Okay.
Okay, the 45 minutes flies by. Let me, so I'm going to be very brief for the second part. So recall the second part was that we have 1 minus epsilon good people. The good people, even within the good people, there are some corruption inside their sample set, so their sample set are not quite trustworthy. If I just simply use the sum of the squares with like a giant batch, my error would be proportionate to beta plus epsilon, but hopefully we want to get this square root beta. So we want to be, our error should be proportionate with this part and not this whole thing. And again, there is an epsilon over n in here, just beta would be always larger than that, so that term does not show up here. So the technique is very similar to what we saw in the first step. What we do is first run a crude estimate. So we essentially think of it as we solve two sum of the squares simultaneously. The first one takes all the samples as one giant batch and try to run a standard sum of the squares over it. And this will help us to essentially get rid of a very bad elements or very terrible outliers in the batch. So it will replace some of the elements. And then based on the people that sum of the squares, the first sum of the squares, like I just want to say I'm going to refer to them as first and second sum of the squares, but there's one sum of the squares, it's just two blocks of polynomial equations. But the second part, what it does, it essentially try to look at the elements that at least 1 minus beta fraction of their samples are not corrupted, and then use their mean only on the parts that is not eliminated by the first set, and use that mean as a sample. And this sort of brings us back to the previous case. So now I have sort of empirical mean per user that is going to be the right sample. So here, for example, the Zij's are essentially the estimation from the first set, and then I have this Yi, which would be the imaginary good empirical mean per user. And again, I'm going to quickly skip this, but basically, if you come up with two nice sort of balanced truncation for both parts, you're going to get both results that you want. I'm going to also skip this one, but this is the final error term. And again, this term is just eliminated. And let me talk quickly about the hardness result as well. So basically, the idea is very similar here. I allow for alpha fraction. So this is like H3 is just all zeros, and H2 has alpha math on one. Oh, shoot. Yes, you're right. This should be beta. Yes. Yes, so there is like 1 minus beta fraction here and beta fraction here. So in expectation, you would expect that beta fraction, and also I think it should be beta over 100 or something, so I'm not precise on the constant. But essentially, per user, you would expect that only beta fractions are corrupted. And if you allow for constant many, like you can show with simple Chernev bound that the probability that you would need more than beta is probably bounded by a constant, given that beta is at least 1 over n. And then if you allow even for constant corruption, you would need the square root beta to distinguish these two cases. I I think I'm gonna also, so this was the part that I wanted to give a little bit of intuition about the identifiability part, but I'm gonna skip and end here. Thank you very much.
Any question?
Just a quick one. I have another one, but I'll ask you offline.
Sure.
The convergence time, the SOS.
Oh, bad. It's like polynomial, but basically
But
it's
not exponential.
it's not exponential. Polynomial, but it's I think it's I think yes, power 6.
That's fine.
Yes.
Because you're avoiding the depth function.
Yes.
And so just wondering how much are you gaining from avoiding that?
Yes, so it is a polynomial. Both of them are polynomial time algorithm, but they are not pleasant polynomial algorithm.
Okay, any more questions? Okay, if not, oh.
So, if we didn't have like, if alpha were 0, so everyone was like, no, sorry, not alpha. If epsilon were 0, so everyone was like nice, but they had like some beta fraction samples which were corrupted, then I think the truncation estimator with the truncation level dependent on beta is known to be tight. So is the two-level thing sort of trying to do the following? Basically, instead of putting the MLE estimator as a constraint in the SOS constraints, you want to put the truncated estimator as the constraint?
No, it's just when you write those terms, I think one thing, like maybe if I give this intuition part. So so this is for a standard robust mean estimation, but essentially you are trying to work on z bar minus z bar squared, so this term. And what happens in there is that you write it based on how much things are equal. So you only need to consider the contribution of the terms that are different. So you would get this epsilon factor that comes from that part. And then you have this squared all through distance. And this is the part that you can write it in terms of the mean, like the distance to their own mean, and then the vector of the difference of the means. And playing with that, the variance will pop up. I'm not sure if I understand what you mean by putting the truncated as the MLE.
Not completed. Well, maybe I'll take it off.
Okay, sure.
Conflating two things.
No problem. Okay.
Okay, thank you very much for your talk.
Thank you.
Right now we have a group hike, so we will meet in front of Simon's in 5 minutes.
Some quick question.
Oh, sure. Let me just, sorry, turn off this one.
If on the
I think we did the shorter.